AlexNet. AlexNet was the winner of the ILS-VRC image classification competition in the year 2012. The main motivation behind AlexNet was to build a deeper network that can learn more complex functions. And we have already seen the LeanNet which performed very well on the MNIST dataset. But it turns out that the MNIST dataset is very simple because it contains grayscale images, that is one single channel, and classified into only 10 classes, which makes it a simpler challenge. But now in 2012, Alex, Geoffrey Hinton, Ilya, all the three of them together, they created a neural network architecture called AlexNet. And they published the paper with the title ImageNet Classification with Deep Convolutional Neural Networks. They trained their network on 1.2 million high-resolution images into 1,000 different classes of the ImageNet dataset. AlexNet was the state-of-the-art at its time, that is in the year 2012, because it was the first real deep network at that time in year 2012. And it opened the door for the computer vision community to seriously consider convolutional networks and their applications. Here is the AlexNet architecture. As you can see from this picture, AlexNet has a lot of similarities to LeanNet, but it is much deeper, that is more hidden layers, and also bigger, that is more filters per layer. And both AlexNet and LeanNet, they have similar building blocks of a series of convolution plus pooling layers stacked on top of each other, followed by fully connected layers and a softmax at the end. And we have seen that LeanNet has around 61,000 parameters, whereas AlexNet has about 60 million parameters and 650,000 neurons. And this gives AlexNet a larger learning capacity to understand more complex features. And also, this allowed AlexNet to have a remarkable performance in the ILS-VRC image classification competition in the year 2012. So, what is ImageNet and ILS-VRC? Well, ImageNet is a large visual database designed for use in visual object recognition software research. And the ImageNet is aimed at labeling and categorizing images into almost 22,000 categories based on a defined set of words and phrases. Whereas ILS-VRC, which is the ImageNet project, which runs an annual software contest called the ImageNet Large Scale Visual Recognition Challenge. The short form is ILS-VRC, where software programs compete to correctly classify and detect objects and scenes. Now back to AlexNet architecture. The architecture is pretty straightforward. It consists of convolution layers with the kernel sizes 11 by 11, 5 by 5, and 3 by 3. And it consists of max pooling layers for images downsampling. And AlexNet also has the dropout layers to avoid overfitting. Here, unlike LeanNet, AlexNet authors used ReLU activation functions in the hidden layers and a softmax activation in the output layer. And AlexNet it consists of 5 convolution layers, some of which are followed by max pooling layers and 3 fully connected layers with a final 1000-way softmax. And we can represent the AlexNet architecture in text as follows. That is, starting with the input image, the first convolution layer, then pooling layer, convolution layer, pooling layer, convolution, and then again convolution, convolution, then finally pooling, then the fully connected layer, again fully connected layer, finally the softmax function. Before AlexNet, deep learning was starting to gain traction in speech recognition and a few other areas, but AlexNet was the milestone that convinced a lot of the computer vision community to take a serious look at deep learning and demonstrate that deep learning really works in computer vision. And if you compare the previous convolutional neural networks like LeanNet, AlexNet presented some novel features and that were not used in previous architectures. For example, the ReLU activation function. So the AlexNet used ReLU rectified linear unit for nonlinear part instead of the tanh or sigmoid functions, and also some of the other various techniques such as dropout layer, data augmentation, local response normalization, and weight regularization. So these are the techniques were used in AlexNet2 for better performance. And the authors used a GTX 580 GPU that has only 3 GB of memory. It was state of the art at that time, but not large enough to train the 1.2 million training examples in their dataset. Therefore, they developed a complicated way to spread their network across 2 GPUs. The basic idea was that a lot of these layers were split across 2 different GPUs, and there was a thoughtful way for when the 2 GPUs would communicate with each other. So, but we don't need to worry about all these details nowadays because there are far more advanced ways to train our deep networks on distributed GPUs. Okay, now that we learned the basic components of AlexNet and the novel features, now let's apply all these together to build the AlexNet neural network. Here is the architecture of AlexNet. As we can see from this picture, the network contains 8 weight layers. The first 5 are convolutional and the remaining 3 are fully connected. The output of the last fully connected layer is fed to a 1000-way softmax, which produces a distribution over the 1000 class labels. AlexNet input starts with 227 by 227 by 3 images. If you read the original paper, we will notice that it refers to the dimensions volume of 224 by 224 by 3 for the input images. But the numbers make sense only for 227 by 227 by 3 images. And some people suggest that this could be a typo error, typing mistake in the original paper. So in this figure, the layers are stacked together as follows. So the first one is the convolution layer. The authors used a large kernel size, which is 11. So they also used a large stride, which is 4, which makes the input dimensions roughly shrink by a factor 4. That is from 227 by 227 to 55 by 55. So let's calculate the dimensions of the output. That is 227 minus 11 divided by 4 plus 1, which is 55. And the depth is the number of filters in the convolution layer, which is 96. So the output dimension is 55 by 55 by 96. The next, pull layer with the filter size of 3 by 3, which reduces the dimensions from 55 by 55 to 27 by 27. That is 55 minus 3 divided by 2 plus 1, which is 27. So the pooling layer does not change the depth of the volume. The output dimension is 27 by 27 by 96. Similarly, we can calculate the output dimensions of the remaining layers. That is convolution minus the kernel size is 5. The second convolution layer for which the kernel size is 5, depth 256, and the stride 1. So pool layer, the next one is the pool layer with size of 3 by 3, which downsamples its input dimension from 27 by 27 to 13 by 13. Then the third convolution layer, in which the kernel size is 3, depth 384, and stride 1. Convolution layer 4, where kernel size is 3, depth 384, and stride 1. Convolution layer 5, where the kernel size is 3, depth 256, and stride 1. Then there is a pull layer with a size of 3 by 3, which downsamples its input from 13 by 13 to 6 by 6. Then the flattening the layer to flatten the dimension volume to 6 by 6 by 256 to 1 by 9216. So then there is a fully connected layer with the 4096 neurons, and again there is another fully connected layer with the 4096 neurons, and finally softmax layer with 1000 neurons. So you might be wondering, how did the authors decide to implement this configuration? See, setting up the right values of the network hyperparameters like the kernel size, depth, stride, pooling size, etc. It's a tedious work of a lot of trial and error. But the idea remains the same. We want to apply many weight layers to increase the model's learning capacity to learn more complex functions. We also need to add pooling layers in between to downsample the input dimensions. And with that said, setting up the exact hyperparameters comes with a lot of trial and error, and this is one of the challenges of convolutional neural net. Here is the code to build the AlexNet architecture. Here you can notice that all the convolution layers are followed by a batch normalization layer, and all hidden layers are followed by the ReLU activations. And here is the model summary. When we print the model summary, we'll see the number of total parameters as 62 millions. To be precise, 62,383,848. In a way, both LeanNet and AlexNet have so many hyperparameters to tune, and the authors had to go through so many experiments to set the kernel size, strides, and padding for each layer, which makes it harder to understand and manage. So setting up the learning hyperparameters for AlexNet. In fact, AlexNet was trained for 90 epochs, which took 6 days simultaneously on 2 NVIDIA GeForce GTX 580 GPUs. This is the reason for why you will see that their network is split into 2 pipelines in the original paper. The authors started with an initial learning rate of 0.01 with the momentum of 0.9. The learning rate is then divided by 10 when the validation error starts improving. And now let's look at the AlexNet performance. In fact, the AlexNet significantly improved all the prior competitors in the ILS VRC challenges and achieved a winning top 5 test error rate of 15.3% compared to 26.2% achieved by the second best entry of that year that uses other traditional classifiers. This huge improvement in performance attracted the computer vision's community's attention. So what is top 1 and the top 5 error rate? See, top 1 and top 5 are terms used mostly in research papers to describe the accuracy of an algorithm on a given classification task, where the top 1 error rate is the percentage of the time that the classifier did not give the correct class the highest score. And the top 5 error is the percentage of the time that the classifier did not include the correct class among its top 5 guesses. Ideally, we want the model to always predict the correct class in the top 1, but top 5 gives a more holistic evaluation of the model performance by defining how close the model is to the correct prediction for the missed ones.